This video will be an introduction to integrals. In it we're going to learn about two main types of integrals, actually the only two types, which are definite integrals, which look like this, integral from a to b of f of x dx. That's the first kind. And the second kind, guess what, is indefinite integrals. And indefinite integrals, the only difference is that there are no limits of integration. These, this a and this b, these are called the limits of integration. And as another note, you might see indefinite integrals. These are also called antiderivatives, and we'll talk about more about what that means in this video. Here we go. Recall from last time that when I say integral, you think area. And so the integral, the definite integral from a to b of f of x dx, this has a physical meaning, and the meaning was the signed plus or minus area essentially between the function f of x and the x-axis between x equals a and x equals b. So if I draw a picture of this, here's a function like that, f of x, here's a, here's b, and essentially this integral has, you add up positive area, negative area, positive area, and whatever the addition of those areas is, that's the value, the numerical value of the integral. And so a definite integral has a significance, its area. In the last video, the way we found this area was to approximate it using Riemann sums with rectangles or trapezoids. In this video, we're going to figure out how to find this exactly. And so what we have to do is we have to figure out what this means. Well, to figure out what this means, we first have to answer a slightly easier question. And the slightly easier question is, what is just the indefinite integral of f of x dx? And this is where the antiderivative part comes in. Check it out. Let's say, for example, that I want to integrate x squared dx. Well, I'm not sure what this means. I don't know what this is yet. It's question mark. Well, the integral is basically undoing a derivative. So this question is the exact same as asking the derivative of what function, in red, gives me x squared. Okay? So when you're doing integrals, think of it not as what's the, like this is the question, what's the answer? Think of it in terms of a derivative. Okay? I have the answer. The answer is x squared. What is the question? The question is, what is the derivative of what function is x squared? Okay? Well, think about it. In order to get x squared, I need to start with a higher power. Namely, I have to start with x cubed, because remember how I like bring down the 3 and then subtract 1? The subtracting 1 is going to get me the 2. But I can't just say x cubed, because the derivative of x cubed is 3x squared. I need to get rid of this 3 somehow. Well, the way I'm going to do that is I'm going to multiply the x cubed by 1/3, because that way that 1/3 will stay through with the derivative and cancel with the 3 that's brought down. Hopefully that made some sense. Essentially what I do is say, okay, I have a 2, I need to add 1 to the power, so it's going to be x cubed, and because when I take the derivative of x cubed I bring down the 3, I'm going to divide by that power. And so the antiderivative of x squared dx is x cubed divided by 3. What? Plus c? Plus c. What is plus c? Let me tell you. The question was, the derivative of what function gives me x squared? Well, we said very clearly that the function was x cubed, or 1/3 x cubed, or x cubed over 3, the same thing. But this isn't the only function that when I take the derivative of it, I get x squared. Think. what if I have the derivative of 1/3 x cubed plus 1? Oh, that's a cube, not a squared. Careful, because when I take the derivative of this, guess what? I'm still going to get x squared. And if I take the derivative of 1/3 x cubed plus 2, I still get x squared. And if I take the derivative of 1/3 x cubed plus any number, any constant number, when I take the derivative of that constant, it's going to go away, and I'm still going to end up with x squared. So, when I do any sort of antiderivative, example here, whenever I do this, this is not the answer, because x cubed over 3 is not the only function that is the antiderivative of x squared. Okay, when I answer the question x squared dx, integral of x squared dx, the answer is not just x cubed over 3. It's x cubed over 3 plus c. This constant is special. It is called the constant of integration. That's right. It's got a name. To further illustrate why the constant of integration is important, here's an example with a graph. Graphs are nice. Let's say I'm integrating 2 dx. Remember that to integrate, we have the answer. The answer is 2. What I really want to do is think about what function, when I take the derivative of it, gets me 2. And if you're thinking 2x, you're probably correct. In fact, you are correct, except that's not the only function that gives you a derivative of 2. We also have like 2x plus 7, or 2x plus 7 million. All of these give you 2. Well, if I think about slope and derivative, really this is a linear function because the derivative, the slope, is always the same. And so when I ask this question, the integral of 2 dx, I'm really asking what functions, plural, all have a slope of 2. And the answer is 2x plus c. And if I think about this in terms of y equals mx plus b format, well, here's one of those solutions. In fact, that's this first one. But really, any vertical translation of this line, all the derivatives of all of these lines are all 2. And so what happens is this plus c just becomes a vertical translation of some parent function. In this case, it's 2x. But that's why we have to include the plus c, because I can shift any original function up or down by a constant and still get the same derivative. Let's do some quick examples of integration. Let's say I'm integrating x cubed dx. Well, if you think about it, really I have the answer. The answer is x cubed. No. The derivative of what is x cubed? Think about powers. Well, to get x cubed, I'm going to have an x to the 4th. And if I bring down that 4, I'm going to have 4x cubed, so I need to get rid of that 4, so I need a 1/4. So the integral of x cubed dx is 1/4 x to the 4th. Don't forget, plus c. In general, for any polynomial, or anything that's in the form of x to the n, and in this case n could be a fraction, a decimal, really anything, except for something we'll get there. Think about it. What did I do? I took 3 and I added 1. So this is going to be x to the n plus 1. So instead of bringing down the power and subtracting 1, I'm going to add 1 and then divide everything by that new power. And so this is like the reverse power rule for integrals, and I have my plus c. But notice that n plus 1 is in the denominator. So actually, n could be anything except one number, and that one number is -1. And we'll get to what happens if n is -1 in a later section. Let's get back to our original question. And the original question is, I guess maybe it wasn't the original question. Anyway, let's say I have the function y equals x squared, and I want to find the area of this function. Specifically, like in the Riemann sum video, the area between 0 and 4, so this area right here. Well, I say area, you think integral. So we're going to integrate from 0 to 4 of x squared dx. Well, I don't need to use rectangles anymore because now I know how to do this. The integral of x squared dx is x cubed over 3 plus c. And so the way I'm going to write this, sorry about that, the way I'm going to write this is like this. We're going to write our antiderivative first. The antiderivative of x squared, use the reverse power rule, is x cubed over 3 plus c. And now these limits are important, and here's how they come into play. They go on the outside of this, these brackety parentheses, and here's what I do with them. I'm going to plug them in. First I'm going to plug in 4 and evaluate the function, the antiderivative at 4. So I'm going to have 4 cubed over 3 plus c minus, and now I plug in 0 for x, and I get minus 0 cubed over 3 plus c. And now I'm going to simplify. And so what I get when I simplify, 4 cubed over 3 is 64 thirds. 0 cubed over 3 is 0, and notice here that the plus c minus plus c, the c's cancel out. And that's nice, and that will always happen whenever you do a definite integral. And so my answer is 64 thirds, and this is in fact the exact area under the curve of y equals x squared. Very nice. Let's just recap what we did to do integrals of this form. So if I have the integral from a to b of f of x dx, my process is to find, essentially I want to find the antiderivative of f of x. And so the way I did that was I thought, well, the derivative of what function was f of x? Hey, just for kicks, we're going to call this blank function capital F. And so really what I have is the antiderivative of f of x is equal to capital F of x, or similarly, the derivative f prime of x is going to be equal to little f of x. And then what did I do with that antiderivative, that f of x? Well, I took it and I did a plus c, and then I evaluated it from a to b, and when the c's canceled, what I was left with was f of b minus f of a. And this result is huge, actually. This is known as the fundamental theorem of calculus. Yeehaw!